This video is on bonding and on more specifically ionic bonds. So before we start about the different types of bonds, we should note there's three types of bonds that we're going to focus on in this unit. The first is ionic, then we'll talk about covalent, and then metallic. Now ionic bonds are bonds between a metal and a nonmetal. Covalent bonds are between a nonmetal and a nonmetal, or multiple nonmetals together. And metallic bonds are between metals. Some different properties that go with each one of these types of bonds. Ionic bonds are all going to be solid at room temperature, have high melting points and boiling points, abbreviated as NP and BP. They conduct electricity when dissolved in water or when melted. So for example, when I put salt in water, so like your ocean, or just making salt water, my ionic bond breaks apart into the two ions, so it dissolves or dissociates in water. And they become ions, so I have sodium plus ones and chlorides minus ones in the water. And because they have charges on them, those charges can carry electrons around, which is your electrical current. And as it carries these electrical current through the water because of the charges, that's how that can conduct electricity. In addition, ionic compounds are going to be very brittle due to the way that they set up with one another. Their charges are going to alternate. They'll become very rigid in a crystalline structure. Covalent bonds, like I said, are nonmetals and nonmetals. These are going to be your diatomics, which we'll learn more about shortly. And they have relatively low melting point and boiling points because they're made up of things that are typically gases and some liquids at room temperature. Finally, we have our metallic bonds. They're metals and metals together. And because our metals here, they're mainly our transition metals, although we do dive into our group 1 and group 2 metals as well. With our metallic bonds, they have the sea of electrons, which is where that d orbital, so all of these transition metals have that d orbital of electrons. And those electrons can kind of move freely throughout, so we call them delocalized electrons, or my sea of electrons. And because of this sea of electrons, they have these specific properties. They can conduct electricity because those electrons are moving freely, and that's what allows my electricity to pass through. They're ductile, so they can be pulled into a thin wire. They're malleable, they can be pounded into sheets. And in addition, because of this sea of electrons and metals, we can heat them up and we can mix different types of metals with other elements. Usually where one is a metal, these are called alloys. So steel is an example of this. Your baseball and softball bats have all these different alloys in them to have different bounce of the softball and baseball off the bat. Okay, so this is another property of metallic bonds. So let's get into our ionic bonds. So ionic bonds is an electrostatic force that holds ions together. Remember that ions are formed by adding or removing an electron to gain a full octet, and this is our octet rule. Here, this rule and ions depend on the atom's number of valence electrons. Remember that your valence electrons are the number of electrons in the highest energy level. So this is easily seen if we number the periodic table excluding my transition metals. So an example of this is shown here. I have my periodic table group 1 and group 2. If I get rid of my transition metals and don't factor those in when numbering, then group 3, 4, 5, 6, 7, and 8 being my noble gases. My first three groups, 1, 2, and 3, well, it's easier for them to lose those 3 valence electrons to get down to 8. Group 4 can either go either way. Numbers above my staircase line, those are nonmetals, so they're going to gain electrons. Numbers below my staircase, those are considered metals, so they're going to lose electrons. And then my nonmetals, group 5, 6, 7, and 8, they're going to gain electrons, although 8 is your noble gases, so they're just inert. They're not going to gain or lose electrons. So remember that metals lose electrons to become cations, and nonmetals gain electrons to become anions. Because of my cations, my anions, my positively charged parts, my negatively charged parts, an electrostatic force can occur. This is between a positive and a negative atom. So my cation actually donates electrons to the anion so that both achieve a full octet, again fulfilling my octet rule. So let's practice what kind of ions will be made from these different atoms. So my first one I have is calcium. You want to locate calcium in your periodic table. You should find that it's in group 2. So because it's in group 2, it's going to lose these 2 electrons and become calcium plus 2. Okay. Sodium is in group 1. Therefore, sodium is going to become Na plus 1. Go ahead and try aluminum and francium. Next we have our nonmetals. I have fluorine. Fluorine is in group 7, therefore it's going to want to gain 1 more electron and become fluorine minus 1. Chlorine has the same thing. It's again in group 7, so it's become chlorine minus 1. Go ahead now do sulfur and phosphorus. Now we have a specific way to name our ions. Cations, they have the name as same as the element, always add ion at the end. Anions have the element stem, and they have an IDE ending after the stem. So let's try naming our cations. These are positively charged. So for my calcium plus 2, I just call that a calcium ion. Sodium, again, is just a sodium ion. Aluminum and francium, again, just cations, so I just use my element name. The other elements that I have turn into anions. Now anions, I use my element stem with my IDE ending. So for fluorine, the stem on that is fluor. So I now have F-L-U-O-R, that's my stem, and I add my IDE ending. So it becomes a fluoride ion. Same thing with chlorine. Instead of it being chlorine with the I-N-E ending, I change the I-N-E ending to I-D-E. So it becomes chloride. Go ahead and try sulfur and phosphorus. You should have got sulfide ions and phosphide ion, not phosphoride, just phosphide. So now let's go ahead and combine our cations and anions together to make my ionic bond. So to do that, we can show the electrons actually being donated from one to the other. So let's start with sodium. If I'm adding sodium plus chlorine, first I want to know what ions are going to form. Well, sodium is a plus 1 ion because it's in group 1, so I'm going to have sodium plus 1. And then I'm also going to have chlorine minus 1. Then I'm going to go ahead and draw the Lewis dot diagrams. You have examples from that in the POGL that we're going to do. All we do is draw our electrons as dots, our valence electrons, around my atom. So sodium is going to be Na with 1 dot for its 1 valence electron. Chlorine is going to be my Cl with 7 dots for its 7 valence electrons. Notice that this also matches up with its group number if I exclude my transition metals. Next, I'm going to show sodium giving its electron to chlorine, which is this going to make it an ion. So chlorine wants 1 electron to fill its octet. Here is the hole, so sodium is going to donate its electron to chlorine, therefore making it sodium giving its electron to chlorine. And now sodium has a +1 charge and chlorine has a -1 charge, thus the positive-negative electrostatic interaction between them. Here I notice what my ratio is of sodium ions to chloride ions, and I have a 1-to-1 ratio. So to write my actual chemical compound, I write sodium chloride, NaCl, one of each. Example 2, I have calcium and chlorine. Well, first I want to figure out what kind of ions do they want to form. Calcium's in group 2 with 2 valence electrons, so it's going to want to get rid of those 2 electrons to be calcium +2. Chlorine's in group 7, so it's going to want to gain 1 electron. Then I draw my Lewis dot diagram. I have calcium with my 2 electrons, and then I have chlorine with its 7. Next, I show calcium giving its electron to chlorine, which forms the ions. So I take its electron, and I go ahead and give it to chlorine. But now calcium has 1 extra electron, and it's still not satisfied with having a full outer shell. So I need to incorporate another chloride ion. Again, I showed 7 valence electrons, and now its electron is donated here. Now everybody has either an empty outer shell, which then gets removed, or a full outer shell, like chlorine. I count my number of calciums of chlorine. I have 1 calcium to 2 chlorines, so I put my number of how many I have as subscripts by my elements. So I have calcium chloride, CaCl2. Go ahead and try aluminum plus chlorine. You should get AlCl3. Notice and look back at the ratio of ions. The ratio of ions to each other is the same as if you crisscross the ions' charges. So here we look at calcium and chlorine like we just made. Calcium +2, chlorine -1 ends up making CaCl2. So if I took my charges and I crisscrossed one down to the outside of the other, my 1 would come down here, and my Cl2, my 2 for my calcium would come here, and I'd have CaCl2. I don't have to write the 1, it's implied, so I just have CaCl2. Again, if I have magnesium, which is a +2, phosphorus, which is -3, I can crisscross my charges down and down, and I have Mg3P2. So again, just crisscrossing down the charges. You can confirm this by drawing that Lewis dot diagram of the interaction between them. Go ahead now and try aluminum plus chlorine. You should have gotten, again, AlCl3. Now, what about naming our ionic compounds? Well, to name them, they're always a metal plus a nonmetal, so therefore, it's a cation plus an anion. Well, how do we name cations? Well, it's just my element. Anions is my element stem with an IDE ending, so we name ionic compounds the same way. Here I have aluminum, 2, sulfur, 3. So I write that as aluminum is my cation. So I write aluminum. And then I go ahead and write my anion, which is sulfur -3. Sulfur having the stem of Sol. And then my IDE ending. So I get aluminum sulfide. Here I have sodium and chlorine, my sodium ion and my chloride ion. So I just pair them together of sodium and chloride. Go ahead now and try writing the name for CaCl2 and Mg3P2. You should have got calcium chloride and magnesium phosphide. to go the opposite direction. Given the name, we should write the compound from the names. Potassium fluoride. Potassium is K, fluoride is F. I then check to see what their charges will be. Potassium is in group 1, so it's going to have a +1 charge. Fluorine is in group 7, so it's going to have a -1 charge. My charges are going to crisscross down, and I get KF. Next, I have beryllium nitride. I do the same thing. I have beryllium, Be, and I have nitride, which is just my nitrogen. Notice my nitri is my root, my stem for nitrogen. Beryllium becomes a +2 because it's in group 2. Nitrogen is in my group 5. This is going to have a -3 charge. They crisscross down, and I get Be3N2. Then I have calcium sulfide. Again, I write my calcium, and sulfide, that gives me sulfur. Calcium's in group 2. It's going to lose those 2 electrons and become +2. Sulfur, again, is in group 6, so it's going to gain 2 electrons. So Ci +2, S -2, crisscross down, and I get Ca2S2. Now, just like in math, when I have 2 numbers that are divisible by the same number, I can reduce them. So both of these are divisible by 2. 2 over 2 becomes 1 for each. So I get CAS as the same thing. You should reduce them, and you are required to reduce them in order for it to be correct on a test or in anything with chemistry. So go ahead now and try the following: lithium bromide, aluminum oxide, and aluminum phosphide. You should have got LiBr, Al2O3, and for the last one you should get Alp because both have a positive and then -3 charge, which get canceled out.